Hello everyone, my name is Luca Bertaccini and I am a PhD student at the Digital Circuits and System Group at ETH, and I'm part of the pod team. I am originally from Italy and I moved to Zurich in March when I started my PhD under the supervision of Professor Benini. My journey brought me here today to present a tiny RISC-V floating point unit. So nowadays we are living the era of Internet of Things, where billions of devices are gathering data and sending them to servers. To save bandwidth and energy across the whole network, processing on the edge is necessary. And since more and more processing is done on the edge, and many existing algorithms needed on the edge require floating point arithmetic, small and efficient core that we implement on the edge need to support floating point arithmetic. So small cores, area-optimized core, occupy 10-20 kilogate. And we have two solutions if you want to support floating point arithmetic. Either to add a floating point unit, so to support them via hardware, or to have some software emulation functions that will emulate the floating point instruction on the integer data path. So in the first case, floating point units introduce a large area overhead, and for a single precision floating point unit, this overhead will amount up to around 20 kilogate, while for a double precision implementation will amount up to 50 kilogates, which is more than twice the area occupied by the area-optimized integer core. If we decide to go for software emulation instead, we have a large code size overhead because full software emulation libraries occupies around 5 kilobytes for single precision support and around 15 kilobytes for double and single precision support. So this would also require more system memory and so still has an impact on the area. So we have seen that we can either implement a full-fledged FPU that introduces a large area overhead, or software emulation, which introduces a large code size overhead. Neither of these things is affordable for low-cost microcontrollers, and therefore we came up with the idea of a tiny floating point unit to support floating point arithmetic, adding a low hardware over area overhead. So we kept Snitch as a host system. Snitch is a 32-bit core that has been designed here at ETH by my colleagues, and it supports both single and double precision extension for floating point. This core has been designed for high performance, and this is why it is coupled with a high performance FPU that occupy a large area. This FPU is optimized as well for high performance and energy efficiency, and has been designed at ETH. So however, the floating point unit is really large. The integer core is optimized for area, so it's a really tiny core. And this is the reason why we decided to keep it as a host system for our Tiny FPU, and to achieve a very small core that supports floating point through a hardware floating point unit. So we started analyzing the native FPU inside Snitch that we will call fast FPU. This is a modular FPU, which means that it's composed by some hardware blocks. Each operation group has a dedicated hardware block. So we have a module for floating point addition, multiplication, subtraction, fuse multiply and addition, and so on. We have a module for comparison, and we have a module for conversions. And this is multi-format FPU. In particular, we were interested in its double and single precision versions. It introduces a large area, and it's fully combinatorial. And we investigated a bit more this design, And we started from the ADMUL operation group because the module dedicated to this operation group was the largest one. So this module required large adders, multiple large adders, multiple large shifters, and one large multiplier. So it's fully combinatorial, and this is why fast FPU can achieve single cycle execution. And its combinational path is, for this reason, quite long. So we started from here, and we asked ourselves, how can we optimize niche FPU for area? So our implementation, Tiny FPU, basically trades area for latency. We were interested in double precision and in single precision, so we decided to design two versions of the Tiny FPU, one with double precision support with single precision included as well, and one just for single precision. The rationale behind this Tiny FPU was to have iterative and multi-cycle execution to reuse data path resources in a time multiplexed fashion. This multi-cycle execution could also allow us to reuse the internal register we introduced in the Tiny FPU. So as said, we started from the fast FPU. We took its components. For example, here there is a large adder, and we tried to realize the same arithmetic operation that was carried out by the large adder with smaller components. So for example, in this case, we divided the adder bit width by 3, and we obtained 3 different adders that, as you can notice from this slide, they are actually the same adder repeated 3 times. So if we decide to go for multi-cycle execution, we can just use one of them and iterate on it. So this is the final solution we achieved with Tiny FPU. We started from the fast FPU components, from the multiplier, which is a p by bit multiplier, where b is the mantissa bit width with the hidden one included, and we reduced its bit width to p by 2. Then we took the large adder, and we divided its bit width by 3, and we did the same for the shifter. Then there were some other small components that has not been further optimized because they were already really tiny. And then we introduced some internal register and an FSM. This is the overhead we pay for time multiplexing. So we have some registers to store the partial results. And we have the FSM, where the control logic is selecting every cycle from the registers, the input that then will be given to the arithmetic components. Since we have this multi-cycle execution, we could also reuse the components. So as in the schematic, we had just one large multiplier. The other one in the figure is the small multiplier. We had just one large adder, sorry, for the mantissas, and one small adder for the exponent. We didn't have, therefore, to have multiple components. Then we realized this for the ADMUL operation group, and then we concentrated on comparisons and cast instructions. They did not require any additional arithmetic components. And for this reason, we added just some control logic to the FSM, and we reused the data path resources we already instantiated for the ADMUL operation group. We decided not to include support for floating point division and floating point square root. The reason is that these two functions are not often used, and the dedicated hardware to support them would introduce a large area overhead. For this reason, we decided not to support them. The good thing about it is that GCC compiler provide an option, for example, not to include the floating point division when it compiles the code, and when it finds a floating point division, it will directly replace it with the software emulation function for division. So we then investigated the results in terms of latency of our Tiny FPU, and in case of fuse, multiply, and additions for our single precision implementation, it takes from 21 to 24 cycles, while for the double precision implementation, it takes from 36 to 39 cycles. We added, as said, the single precision support to the double precision data path at a cost of one extra cycle whenever a multiplication is required, so just for fuse, multiply, and addition, and for the multiplication, while we are really fast in computing comparison and cast, since these instructions are simpler. To evaluate our Tiny FPU, we then considered 5 snitch implementation. First of all, we considered the integer-only core snitch with the software emulation function provided by libgcc. So this is the integer core with software emulation. Then we coupled the integer core with our double precision Tiny FPU and with our single precision Tiny FPU. Finally, we considered the other 2 systems, which are snitch with its native double precision fast FPU and with its native single precision fast FPU. To evaluate each system, we use different benchmarks, both synthetic and real benchmarks. The synthetic benchmarks are made by 2 matrix multiplications, one integer and one floating point. So changing the size of the integer and of the floating point matrices, we were able to tune the floating point intensity of the program. We ran benchmark with percentage of floating point instruction from 0.07% to 53%. As regards the real benchmark, we used FUN, an extract of the fast artificial neural network. We used a 2D convolution, the KNN algorithm, K nearest neighbors, which is a pattern recognition algorithm, and a fixed point version of FUN. So as for the first 2 real benchmarks, the percentage of floating point instruction is around 20%, while for KNN is around 7%, and there are no floating point instruction in the case of the fixed point FUN. We then synthesized our implementations. We targeted 100 megahertz. This is a common frequency for low-cost microcontrollers. And we used the GlobalFoundries 22 nanometer technology. So our Tiny FPU itself, is 53 and 37% smaller than the fast FPU, respectively for double and single precision. However, this is not the only area overhead we have when we want to support a floating point via hardware. RISC-V defines different register file for integer and floating point data, and the floating point subsystem had a large area overhead not dedicated to the floating point unit. This is the orange part in the error result, and 70% of this area is dedicated to the register file. Then we have some decoding, we have a load store unit, and some registers that are distributed around the floating point unit. The blue part is instead the integer snitch core. Of course, if we do not introduce hardware support for FPU, then we get a smaller system, but we pay this price with code size, first of all. Indeed, software emulation functions can occupy up to 15 kilobytes in the case of support for single and double precision, and 5 kilobytes for single precision only support. In our case, we had just to introduce the support for floating point division and floating point square root. So we still had a code size of red, but it was reduced by 79% with respect to the code size of red introduced by the full software emulation library. We then evaluated the performance of our systems. In blue is highlighted the system formed by snitch coupled with our Tiny FPU for double precision. We ran these benchmarks both for single and double precision. The trends we found were similar, so today I will show just the double precision case and the results that we got, but I will comment also the results for single precision. So in this case, we have interesting results because snitch tiny is up to 18.5 and 15.5 faster than the integer-only core when we consider 53% of floating point instruction. So 18.5 for double precision and 15.5 for single precision. Another interesting point is around 5% of floating point instruction. In this case, we are 5 times and 3 times faster than snitching, respectively for double and single precision, while being only 1.3 and around 1.2 times slower than the version with the fast FPU. We then evaluated the power consumption of our system. After, for more than 16% of floating point instructions, there is a steep increase of the power consumption of the snitch system coupled with the fast FPU. This is due to heavier system resources utilization. There is also the reason why the system, including the fast FPU, can achieve such high performance. When we consider again high floating point workload, so 53% of floating point instructions, we found that the snitch coupled with Tiny FPU is up to 47% and 33% less power consuming than snitch coupled with a fast FPU, respectively for double and single precision. Finally, we evaluated the energy efficiency of the systems, and we are not as energy efficient as snitch fast. This is due to the multi-cycle execution, but we are still 8 times more efficient, more energy efficient than the integer-only version of snitch. And there is space for further optimization because, as we saw in the area result, the floating point register file introduces a large area overhead. Currently, there is a RISC-V task group. The task group is ZFNX, which proposes to use just one register file for both floating point and integer data whenever they share the same word size. So this is not standardized yet, but if we implemented this solution to the snitch implementation coupled with single precision Tiny FPU, we would achieve a system that supports floating point through a hardware unit that is just 1.7 times larger than the integer core. The snitch integer core. So to conclude, we presented the Tiny FPU is a new area optimized RISC-V FPU. It's 53% and 37% smaller than a high performance and energy efficient FPU, respectively for double and single precision. And then we evaluated the custom performance of different floating point supports, keeping snitch as a host system. And snitch coupled with Tiny FPU is up to 18.5 and 15.5 times faster than Snitch employing software emulation, and 8 times more energy efficient than the integer-only core. At the same time, Snitch coupled with Tiny FPU is respectively for double and single precision 47% and 33% less power consuming than Snitch coupled with the fast FPU. As a future optimization, we will work on a ZFNX version of Snitch Tiny 32 to achieve the lowest area overhead to support floating point in hardware. So as everything we do at Pulp, this Tiny FPU is going to be open source soon. And if you want to be up to date with all our project and open sources release, you can just follow us under our website at pulpplatform.org. And to conclude, I wanted to thank my colleagues at ETH that were involved in the project and the Huawei team that supported us in the Tiny FPU project. This concludes my presentation. Thank you for the attention.